So I'm going to talk to you about Bayesian affect control theory, but actually I'm going to spend most of this talk talking to you about artificial intelligence. And the reason I'm going to do this is because I think that I want to give you my perspective on this whole thing, and I think that it will provide a sort of an alternative, a bit of an alternative view, a viewpoint into Bayes Act, into some aspects of the model that maybe are not in the forefront of a lot of your minds. In particular, the relationship between Bayes Act and rational utility thinking and decision theory. Okay, so my background is in artificial intelligence. So about 25 years ago, I started working on, my dream became one of creating or understanding human intelligence by trying to create it. Okay, so that's basically what people working in artificial intelligence are trying to do. And artificial intelligence has seen a huge number of huge successes over the last 50 or 60 years, and I'm just showing a little collage of some of them here. You can see Garry Kasparov playing Deep Blue in the background, which was this momentous event in the history of AI, when the computer beat the world grandmaster at chess. You can see IBM's Watson playing Jeopardy, which was another big success story for them. And then recently we have the computer Go player that beat the world champion, so this was a Google product. In the middle, you can see the Google self-driving car, which arguably is one of the most amazing pieces of artificial intelligence that we have, and it's really potentially going to really revolutionize our world. One of the things about artificial intelligence, though, is that most AI has absolutely no model of humans. Okay? So Google cars have a problem when they get to busy intersections, and these busy intersections are a problem for them because they can't display enough aggression to get through the intersection. All right? And that level of aggression is something that is culturally specific. Depending on where you are, it's going to be different. Right? And so this comic by the Oatmeal sort of shows that. So here's a Google car trying to negotiate passage through an intersection with a human, and the human's saying, are you going or should I go? And the car is saying, you go first. And the human's saying, what if I point a lot and flail my arms around? And the car is saying, this is confusing. And so the Google car has no model of how a human works. Okay? So it has no way of dealing with this situation. And so it's quite remarkable that this artificial intelligence, people have been working on this for a long time and have been doing it without even thinking about human beings. And when you think about the fact that we as humans, our intelligence is probably largely taken up with figuring out what other humans are going to do, this is kind of weird, right? So to understand why this is the case, we have to go back and look at artificial intelligence in history. So I believe, so artificial intelligence was essentially founded, or the core principles were laid out by this mathematician, John von Neumann, who was an extremely prolific scientist. And he wrote this book called The Theory of Games and Economic Behavior, in which he invented game theory and decision theory. So I'll talk a bit about decision theory over the course of this talk and tell you a little bit what it's all about. John von Neumann was a truly remarkable man. He did a number of different things, a number of different inventions, the other one being the modern digital computer. He was the one who laid the foundations for it and invented the computer architectures that we all use today. And here I'm showing the EDSAC, which is probably the first implementation of the von Neumann architecture machine. Dartmouth has a very interesting connection to artificial intelligence. So in 1956, a young assistant professor by the name of John McCarthy, that's this gentleman here, sent out an invitation to all sorts of famous cognitive scientists and various other scientists who were working in a number of different fields, and invited them to Dartmouth for 6 weeks in the summer of 1956 to try to hash out what artificial intelligence was. Okay? And he sort of coined the term artificial intelligence. And so this picture is from their 50th reunion, which they had here in 2006. And you can see this is the letter that he wrote to various people. So he's offering them $1,200 to come to Dartmouth. And he says the dates are June 18th and the place is Hanover, New Hampshire, in parentheses, a cool place. Right? As we've all found out. Okay, so then artificial intelligence, not much happened until I came along and started my PhD in 1996. I worked in my PhD on building this robot that was a robotic waiter. And the robot would wander around. His name was Jose. and he would wander around at a reception with this tray of food and offer food to people. Okay, so it had abilities to find people, go up to them, and then say, would you like an hors d'oeuvre? So we took this down to this robotics competition in Seattle in 2001, and we won the competition. And so then we came back and were showered with glory and invited to Ottawa so that the Minister of Technology at the time could show off how great his programs were working and things like that. I'll tell you two things about this robot that are kind of interesting from a more of a sociological perspective or social psychological perspective. The first one was before, so Jose the robot doesn't actually look like this. He's just a sort of tube of steel, right? And right before the competition, the first round, myself and another guy, one of the other students that was working on it, we said we should really dress this guy up. So we ran out of the convention center in Seattle, and there was a Salvation Army right across the street, which was quite convenient. And so we bought this crappy suit, and we dressed him up in the suit. And I believe that that's why we won the competition. One of the reasons. Because he looks like a waiter. Talk about identity, right? I mean, this is what people expected. Our competition, one of the other ones, was from sort of a garage robotics group in Seattle, and theirs was an upside-down garbage can. So you can imagine how ours would take the cake as far as looking like a waiter. The other story was that we programmed in a funny behavior where the robot would wander around, and if somebody reached out and grabbed an hors d'oeuvre without being offered one, it had a few things it would say, like it would say, stop stealing, or that's bad, give me back that hors d'oeuvre. And the reactions of people to this were hilarious. I wish I'd been videotaping it, because they'd be sort of, engaging, talking to somebody and about their grant proposal or whatever it was, and then the robot would come wandering by and they'd reach over and pick something up and it would say, stop stealing, that's bad. And they would go, oh, I'm sorry, and they would put it back and apologize to the robot and then turn back without batting an eye, without even realizing the fact that they just said sorry to this robot, right? And go on with their... So this made me realize that, interacting with humans, building machines that interact with humans is a really challenging problem, because you need to have a model of the human, right? So after I worked on this, I did my PhD, then I went to Toronto and started work on systems to help people with Alzheimer's disease to get their hands washed, which I'm still working on, and Linda's involved in this as well, and Catherine now as well. And there, the problem is even more difficult, because the humans that you're interacting with don't really know who they are. So we can talk about this more probably a bit later today or tomorrow. But certainly, I was in Toronto working on this, and then I went to Scotland, and I was in a department where there was a lot of designers and people working on human factors. And I started studying this problem of how do I build a model of a human being and put it inside this machine so that I can build computers that are going to interact with people. And so when you start doing this, you start realizing that humans are very, very complicated, and these models just grow and grow and grow and become things that you just cannot operate with. You can't build a robot that has a model of a human being, right, if you try to take all these factors into account. But I sort of had this feeling that there was something else going on, right, so that when I meet people, it doesn't feel difficult. It feels like I kind of know what to do, right? So with a little bit of introspection, I sort of felt like there's got to be something else going on here. And in my sort of simplistic way of seeing things, I sort of thought, well, maybe it's some kind of extrasensory perception, right? So I somehow we're all communicating with each other through some kind of weird waves that were ascending between our brains. And so I was sort of trying to hash out the details of what that might be. Then I moved to Waterloo in 2010. And in 2011, Paul Thagard, who's a professor of philosophy at Waterloo, now professor emeritus, held this little mini conference called Ignorance Day. And Ignorance Day, you were supposed to go and talk about something that you didn't know anything about, okay? And of course, it was Paul's idea to try to, his goal was to try to mix people up in different disciplines and get sort of multidisciplinary cooperation going on. So I went in and gave a talk, and you can see me here, and my talk was entitled, How Can I Tell What My Wife's Mood Is Before I Open the Door? Okay? And so being pre-tenure, you can't go and talk about extrasensory perception anywhere unless it's at Ignorance Day, okay? Because if you do, you would probably just get sent to the recycling bin pretty quickly. And this has happened to people who talk about ESP. So anyway, so I gave this talk and I said, yeah, I know, somehow I'm able to, I don't have to figure everything out, I kind of know. And then after the talk, this German guy comes walking down the aisle and he looks at me and says, I know the answer to your question. And so that German guy was Tobias Schroeder, and we sat down and had a lunch together, and then he explained affect control theory to me. So then I was applying for tenure at the time, so then I spent the next year, I sort of put it on a shelf, and Tobias says that he sort of thinks I thought I'd forgotten about it and he'd never hear from me again. But I'd gotten a copy of Dave's book, and so about a year later, I opened it up and started reading through it, and the first 10 chapters made no sense at all to me. I was just, and not being a sociologist, having no background in this, not that it wasn't well written, Dave. It's very nice, the first 10 chapters, but I had no context to interpret this stuff in. And then I got to chapter 11 and opened up the page, and I saw this equation, which is that d is equal to f minus tau squared. And I said to myself, that has got to be the potential of a probability distribution. That was the first thing that popped into my mind. I said, there is a probabilistic model here, which has not been uncovered in this book. So since then, I've sort of basically, this has taken over my life and my research career, and this is what I've been working on since 2011, and have enjoyed a lot of success with it. In 2014, I believe, Tobias and I packed up Tobias on an airplane, and we flew down to Bloomington and met with Dave Heiss. And this was, I think, one of the most, really the most enjoyable 3 days of my research career was that meeting with Dave in Bloomington. And Tobias and I flew to Indianapolis and drove to Bloomington, and we stayed in the inn. I can't remember what it's called, the inn right in Bloomington, the Grant Street Inn. And there was a big snowstorm. It was the middle of the winter, and we were supposed to go out and meet Dave at his house. And he said, don't do that. The roads, you won't make it out here. And so I'll come in and meet you. And so each day, Dave would drive in, and we would sit in the breakfast room at the Grant Street Inn and talk about affect control theory. And it was truly a really remarkable sort of intellectual experience for me. And I came armed with all these different questions about the theory. And Dave, I remember him looking at me and saying, when he had started sort of writing down the theory originally in the 60s, he said he'd come up with the answers to all these questions. And he looked at me, I'll never forget, he said, you're the first person who's come along and asked these questions. So I was very touched by that moment, and I'll never forget. Okay, so what I'm going to do now is I'm going to switch gears a little bit, and I'm going to give everybody a crash course in probability and decision theory and in artificial intelligence. So after this little mini crash course, you guys are going to be able to go off and program your own artificially intelligent robots according to the way that people do it now. The first thing that we need to talk about is probability. So there are two views of probability that I'm sure you all know. There's a frequentist view, and there's a Bayesian view. The frequentist view, so let's say we're trying to estimate the probability. We have a coin. I think I have a coin in my pocket. So I have a coin, and I need to know whether or not if I flip this coin, it's going to come up heads or tails. Okay? So if I'm a frequentist, I believe that my uncertainty about the coin is ontological. So it's actually a property of this coin. Okay? And the probability that it will come up heads, in order to figure that out, I've got to flip the coin a whole bunch of times. I flip it a bunch of times, count the number of times it comes up heads, and then that's divided by the total number of flips, and that's the probability that it will come up heads. The Bayesian view is uncertainty is epistemological. So it is not a property of the coin. It is a measure of my belief about the weightedness of this coin. Okay? So in order to figure out whether it's going to come up heads, I just look at my own belief, which could be constructed by flipping the coin a bunch of times. I could change my belief about it if I want. Or it might be constructed from all sorts of other things, right? Like people flip all sorts of stuff nowadays. I have no idea why, but my kids spend most of their days flipping water bottles and trying to get them to land on their end. Okay, so maybe I've watched that a little bit, and that's influenced my thinking about coins and weightedness of coins, or probability of coins coming up heads. So in Bayesian affect control theory, we definitely see uncertainty and probability in a Bayesian way. Okay? This is very important for understanding the way that the model works. It is a measure of an agent's belief about the world. All right, so what's a probability distribution? Well, here's a couple of examples of one-dimensional probability distributions. So this is some variate, which I've called x. But this could be the evaluation, the potency, or the activity of some identity, let's say. And this is the probability that my belief in whether or not that variate, E, P, or A, has that value. And these are three different beliefs. So here's one that's very focused. I really do pretty strongly believe that it's 1.5, but with a little bit of variance. Here's one that's a little bit more spread out. So I'm a little bit less certain about what the value of this variate is. And then here's one that's multimodal. So I sort of have two possible hypotheses about what the evaluation or the potency or the activity of this quantity could be. Okay, we can look at probability distributions in 2 dimensions, and then we can think about Scottish hills, for example, and you can think of it as a surface in 2 dimensions. Okay, so these are just useful visualization tools. Of course, what we're doing is thinking about it in 3 dimensions, and then in that case, you have to imagine the probability distribution kind of like a mist, which we can also get from a picture of Scotland because it's so misty there all the time. And so there, the 3-dimensional space could be E, P, and A, and then the mist, the density of the mist, is the probability density at that point. Okay, so thicker, denser mist means that part of the EPA space is more probable. Everybody okay with that? Scottish mists, they'll come back into the talk later. All right. Bayesians, what they need to do is time is unrolling all the time. Interact in affect control theory is a temporal model. It describes how things evolve over time. And Bayesians need to update their beliefs as time goes on. Okay, so how does this work? We will have a prior distribution, which is a probability distribution over whatever it is we're reasoning about, maybe the weightedness of this coin, for example. And what I do is I make a hypothesis about the way the world is going to be after I do certain things, like maybe after I flip the coin. All right? This hypothesis is another probability distribution. Then I receive some evidence, so I actually flip the coin, right? I get some evidence, and I adjust my belief to form a posterior distribution, which is another probability distribution, right? So if I take the coin and I flip it, and it comes up heads, then maybe my belief about the weightedness of this coin will shift slightly towards heads, right? I'll say, well, maybe it's a little bit more, it's not quite fair. But if I flip it again, it comes up tails, then it'll shift back, okay? If I flip it a whole bunch of times, I'll basically get something that's around 0.5, assuming these coins are actually fair. Okay, so let's review. An agent has a prior belief about the world, which I'll write as B. And B is the probability distribution over the possible states that the world could be in. So coins can only be in 2 states, heads or tails, right? So I have a probability distribution over that. The agent makes a prediction about the future, which is a hypothesis, which is governed by this probability distribution, so based on its prior. So what do I think this coin's going to be if I flip it, right? Is it going to be the same weight as what it is right now or a different weight? I don't know. So I could have some distribution over that. Then I observe some evidence, which is the actual result of the coin flip, and it has a likelihood given the hypothesis, probability of the evidence conditioned upon the hypothesis. Okay? So I think that if a coin is fair, then when I flip it, it has a 50-50 chance of coming up heads, right? So my posterior belief then, I want to say, well, what do I believe about this coin now after I've flipped it? And based on my prior beliefs is then given by Bayes' rule, which allows me to invert this conditional probability. So the probability of the hypothesis given the evidence and the belief is proportional to the probability of the evidence given the hypothesis. That's the likelihood multiplied by the probability of the hypothesis given my prior belief, and that's my prior. Okay. Now, what I've drawn here is with these little dashed arrows is one representation of this. And I'm going to change this picture very slightly. I'm going to make the arrows solid, and I'm going to flip this arrow around. After I've done that, this diagram becomes what's called a Bayesian network. And a Bayesian network is a representation of all of the probability distributions and the structures that are involved in computing a Bayesian sequential update. So what are the differences? Well, first of all, I made the arrows solid because that's the semantics of a Bayesian network. They're solid arrows. Dashed arrows mean nothing in Bayesian networks. And I've changed the direction of this one. Now that's important because arrows in Bayesian networks are usually drawn roughly according to the causal nature of things, right? So as time goes forward, the priors are somehow causing these posteriors, right? The state of the world now is somehow causing what happens in the future. And the evidence that I observe is being caused by the state of the world. So if I flip this coin, what I observe is a property of the coin, right? The state of the coin. How weighted is it? Is it fair or not? Okay, that clear to everybody? It's important to get that right, because then once you figure that out, all the Bayesian network stuff becomes very, very clear. All right. So why is Bayes' theorem interesting? Well, it allows you to translate between causal knowledge, which is easy to measure and think about, and evidential reasoning, which is what you really want to do. All right? So for example, I can think about what is the probability. So I have something in my hand. I'm going to take it out of my pocket. I'm going to say, this thing that I have in my hand is a bird. And I can ask you, what is the probability that this bird flies? And you can answer that question, right? Because you know something about birds, and you know some of them don't fly, but the ones that don't fly aren't that small. And so you can probably come up with a number. It's probably going to be pretty high, right? What I want to do then is I see something fly by, and I say, oh, was that a bird? OK, so I know it flies. I want to answer the question, was it a bird or not? Maybe it wasn't. Maybe it was Superman, right? And so I can do that by using Bayes' theorem. So in medical diagnosis, for example, I know how to write down what's the probability of symptoms given a disease. So if somebody has a cold, they have a runny nose and a headache. But I want to know, here's a guy who's got a runny nose and a headache. What is the disease that he has, right? In our case, we're saying, what is the probability distribution? We can encode the probability distributions over behaviors given identities. That's your ACT dictionary, right? And I want to know, I've seen somebody do something, what's their identity? What's the probability distribution over identities? So I can use Bayes' theorem to get that by inverting this probability distribution and multiplying it by the prior over identities, which has been wiped off the screen here. OK, so we need a couple more tools in order to pull this all together. And the next one is going to be provided again by our friend John von Neumann, who, with the help of his buddy Stanislaw Ulam. How am I doing for time here? I'm way over time. I'm OK? I go till 9:15, 10:15. OK. So these guys were working together on the Manhattan Project at Los Alamos. And they were trying to figure out what was going to happen when they detonated a hydrogen bomb. OK? And John von Neumann, as I mentioned before, had invented the computer. And this was an example of one here, the ENIAC, a famous early time computer. And Stanislaw Ulam had spent some time in Monte Carlo at the casino and thought a lot about probabilistic events, random events. And they came up with this idea was that, so in order to figure out what's going to happen when you detonate an atomic bomb, the bomb goes off, and there's this huge chain reaction that happens. Okay? And it's uncontrollable. It happens very fast. And it's highly nonlinear. So you can't apply traditional physics. You can't do it analytically. You can't figure out what's going to happen. And so these guys said, well, what if we just simulate it? We've got these computers now. What we could do is just have a simulation where we imagine all the atoms in the uranium or the hydrogen or whatever it was, and then we just run through and simulate what's going to happen. We know roughly what happens when one atom hits the other. So we can do a simulation and figure out, how bad is this going to be. So they invented this method and called it the Monte Carlo method. And we heard about this yesterday. John was talking about Markov chain Monte Carlo and estimating Bayesian statistics. OK, so let's see what this looks like. So we want to actually represent these probability distributions on a machine and then do calculations with them. So what do we do? So here's our one-dimensional probability distribution. One way we can represent it is using a set of samples. Okay? So we just have a set of points, and each one has a value, xi. And we lay them out like this, and the density of points is proportional to the height of that curve, right? So the denser the points, the more probable is that location. So that's a very simple way to represent an arbitrary probability distribution, right? So you can have multiple modes, you can have anything you want. Okay, we're going to make it a little bit more complicated, and we're going to use weighted samples. So we can do this. So now every sample has a weight. So there's big samples and small samples. And you can think of the big samples are just like a whole bunch of little small samples all at the same spot. Okay? And you can translate between these two representations very easily. The reason you do this is because ultimately what you need when you use a Monte Carlo method is an infinite number of samples. So if you could do it, you would use an infinite number of samples and you'd be all set. You could do it perfectly. But you only have a limited machine. You're using that old ENIAC, and so it only has a limited amount of memory. And so what you try to be, sort of there's this trade-off between using enough samples to make everything work and actually being able to do the calculation. So we use weighted samples. You can get away with fewer samples if you weight them. OK, so with the Bayesian sequential update is now done by, here's our prior distribution, which is this set of samples representing this probability distribution. We make our hypothesis, so we predict what's going to happen in the future. So we have some model about the way the world transforms over time. We shift all the samples according to that model, right? This is like moving the molecules in the hydrogen and making them hit one another. Then we stochastically spread things out. This represents the fact that our uncertainty about the way the world is grows over time. Okay, so as time progresses, we become more and more uncertain about the way things are. We spread everything out a little bit. And then some evidence arrives which re-weights the samples. So the evidence comes in at this point, and this sample gets a lot more weight.
To clarify, we become more and more uncertain as we're projecting into the future, not as actual.
That's correct, yeah. So if I believe that the coin is weighted now, maybe an identity example, I believe that you're a professor now. If I try to imagine into the future, I'll become less and less certain that you'll be I'm sure you'll remain a professor. That's a bad example. A famous professor, that my probability that you'll become world famous is going to increase or become less and less certain.
Because observations help us, just to be clear, like the observations you give us the uncertainties in our projection.
That's right, yeah. So if I run a model forward in time and receive no evidence, eventually I'll just be maximally uncertain about everything. I'll just have no idea what anything is. Evidence is crucial for always collapsing this distribution. OK, so here we are. We have our prior. We make our prediction. We spread things out a bit. And then we gather some evidence which shrinks it down. OK? So this is what Dave was talking about in his quantum physics analogy, is this process of evidence being the thing that collapses these probability distributions down to one or the other. OK? So you don't know whether the cat's alive or dead. You open the door. You get some evidence. It collapses that distribution. Remember, the probability distribution is a measure of your belief. Okay? So that is why, in Dave's example, that's why the cat can be both. I don't know which it is. That means that it actually is both, right? According to my belief. Okay.
Why I need tuna and a body bag?
Buy tuna and a body bag, that's right. Okay. Couple more things we need. We're almost there, so don't worry. We've got all the tools in the toolbox almost. We need to be able to compute expected values of some function v. So v of x is a function which could be, for example, the utility of some situation x, right? How good do we think it's going to be? And I'll talk about utility again in a second. We do this expectation by multiplying our probability of events by the values that they have, or the values of this function, and then summing out over all the possibilities that it could take. So Bayesian decision making is then, I want to know what's the expected value of an outcome, and I will take that expectation with respect to my beliefs about what outcomes are going to be the result of my decisions. All right? So given the probability of the outcome given the decision multiplied by the value of the outcome summed over all the outcomes. That tells me how worthwhile is this decision going to be? Okay, so here's an example. This is a slot machine, and this is the same thing as a coin, right? This slot machine has some, but it's a very heavily weighted coin. Has some probability of winning, which I believe is really low. It's 1%, let's say. Probably not that high, but let's say this one is. And it has a probability of losing of 99%. Okay? So then I have a decision. I can either play or walk away. If I play, then I get the value of winning will be, I'll win 100 minus the 10 cents I had to put in. And if I lose, I'll just lose the 10 cents. My expected value is then the probability of winning multiplied by the value of winning plus the probability of losing multiplied by the value of losing. Okay? So if you do that calculation, you get 90 cents. So the value of playing this slot machine is 90 cents. The value of walking away is 0. I don't spend anything. I don't win anything. Okay, so should I play or not? From a Bayesian decision maker. Which one's better? Yeah, right. I'm going to get 90 cents in expectation if I play, and I'm going to get nothing if I don't. Okay, now we're in a position where we can define rationality. So the rationality, again, our buddy John von Neumann defined what this means. For rationality, you need a couple of assumptions. You need to be able to estimate probabilities of events, and the probabilities have to obey certain axioms. So we haven't talked about the axioms of probability, but they have to be they have to work like probabilities work. And then the agent has to have preferences. So if there's two alternatives, this should be boldface X is preferred to boldface X2. I would rather have the X1 than X2. Okay, so I'd rather have a Ferrari than a Lada. Yeah, what did you say? Yeah, you go. Yeah. Okay, I'd rather have one than the other. Then the preferences have to obey certain axioms. Once I assume those things, I can construct a real valued utility function which assigns a number to every situation X, such that if the utility of X1 is greater than the utility of X2, it means that I prefer X1 to X2. Okay? Once I've set that up, basically what this does is it translates every situation into the one I just showed you before, which is the slot machine, where the utility is just money, right? Everything is directly comparable because I can write it down with a number, and then I can do this calculation of taking the expected utility of every situation by summing over all the possible outcomes. All right? Once I have that numeric function, I can do that calculation and figure out what I should do. Without the numeric function, I can't do that, because all I have are these preferences. Okay. So we put all these pieces together in our Bayesian network, which is our Bayesian sequential estimation machine, okay, with this utility function and the actions that we're able to take, the decisions that our agent's able to take in the world, and we get what's called a partially observable Markov decision process. Okay? So the state of the world is in some state x. We expect it to change to some new state x prime as a function of what we do. Okay, A. So A is the actions of the agent. It changes the state of the world in some way. Then we observe our evidence, which is going to collapse this probability distribution. And then we have a reward function, which I've written R. This is the utility function that tells us which of these things is valuable or not. Okay? So using Bayes' rule, we can then compute these rational choices. This is just the same expectation equation that I showed you before. And we can unroll this in time. So this doesn't stop here. It keeps going, right? We can take the next step and the next step. And we can predict what kind of value we're going to get by taking certain sequences of actions. OK, this is a little bit simpler view of the same thing. If I'm actually going to do this, what I'm actually doing is I'm constructing what's called a plan tree. So this tree is a representation of everything that could possibly happen to the agent as it looks forward into the future. So it's a tree, it's upside down tree. So at its root, it is at its current state. This is its belief. This is its prior belief about what the world state is. Then it has a bunch of actions available to it. And these will make it transition to new states, which are its predictions about the way the world is going to work after it takes that action. All right? And then it observes some evidence, right? And this is somebody else doing something in affect control theory. And that makes it transit to a posterior distribution over the states of the world. All right? But then it can do that again. That posterior becomes its new prior. It can say, oh, then I could do something else. And then the other guy's going to do something else. And that's going to lead me to some other state. And then somewhere down in this tree are these utilities. So now there's some state I'm going to wind up in where I win the game or whatever else. And then I can figure out what that is and propagate those numbers back up through the tree so that I can rank all these actions. I propagate it using these expected value equations. OK. So that's great. Now we know what to do. And at this point, you're ready. You can go off and build yourself your artificial intelligence a robot and take over the world. So, but you're going to run into a problem. OK? You're going to run into this problem very quickly. And the problem is that these branching factors here are colossal, right? A human being, in particular, if we're talking about humans interacting with humans, I have a huge number of possible things I could do. And so do you. Even with a small branching factor, this tree rapidly becomes too big to represent on any machine that we currently have or ever will have. OK? Maybe not a quantum computer, but we'll think about that later. All right. So what can the agent do? Well, it can take certain shortcuts. Like, for example, it can say, well, I'm not going to consider every possible thing that might happen, or thing that you might do. I'm only going to think about the probable things that you might do. I'm going to forget about the small ones because in expectations, they're not going to matter anyways, right? So I can handle that branch there, that set of branches. But this set of branches, I can do nothing about. Because I am in complete control, I can take these actions. And if, let's say I have 10 of them, if I only look at 9 of them, the 10th one might be infinitely more valuable than the other 9. I have no way of knowing that, right? And so I have to expand every single one of these branches. So this is really where the rubber hits the road in artificial intelligence. This is where the big problem is. You have to think about every single possible alternative for your actions. And that basically kills you, right? You can't pull it off. You can't draw this tree out. It'll be too big. OK, so one way to think about this is in reinforcement learning, what you're faced with is not just a single slot machine, but a whole bank of them. And that's like, you can think of this bank of slot machines as being maybe a bunch of people you could interact with, for example, right? Or a bunch of different things you could do to a particular person. And the reinforcement learning problem is you're faced with this bank. Each one of them is like a weighted coin, and you don't know the weightedness of the coin of each one of these slot machines. And you want to wind up in the end playing the one that has the greatest probability of winning. OK? So basically what that means is that branching of that tree, you've got to explore all these different branches. There's one branch for every single one of these slot machines. OK? And so reinforcement learning has a bunch of different techniques you can use in order to figure out, rank these different actions, and make sure that in the end, you're going to minimize your regrets. So in the end, you're going to actually do, as best as you possibly can do, given that you're acting rationally. OK. Right, so that's reinforcement learning. And we'll come back to that in a second. Of course, so maybe I'll give you a little brief hint of what's going to happen. So affect control theory, I believe, gives us a heuristic, tells us which of these machines to go and play. OK? Of all the people we could interact with, of all the things that I could do, it basically illuminates or reveals to me a certain subset of them. And that drastically simplifies my planning problem and allows me to actually do these computations. All right, so to look at that, I want to just mention Descartes' error and the semantic markers. So this book is one that I tell all my artificial intelligence students to read. I'm not sure if they do or not, but never mind. He studied this basic idea where people are able to make decisions based on things that are occurring somewhere in their frontal lobe. And he opens the book with this story about this poor guy who got this giant metal rod stuck through his head, Phineas Gage, and the rod took out a little piece of his frontal lobe. Okay? And after the piece came out, he was actually survived this accident, remarkably, and he was still able to do everything. Like, he was able to do math and compute, do rational calculations and everything else. but his life started to fall apart. And the reason was that he couldn't make decisions. Okay, so Phineas Gage, when confronted with this situation, would dither for hours doing all the calculations that he could in order to figure out what was the optimal machine to play. And he'd never pull a handle. Okay? So there's something going on with these somatic markers, something going on in the frontal lobe, which is basically guiding humans into in their decisions. And it's solving this problem. So I believe that what's happening in affect control theory is essentially that. It's giving us, in human interactions, which are arguably very complex, certainly a lot more complex than figuring out which slot machine to pull, the affect control theory is a model of these somatic markers. Okay, so let's see how that works. Basically, I'm going to take my partially observable Markov decision process, which is my model of the way the world works, and my decisions in it, strictly from a denotative perspective. Okay? The denotative elements, X, are everything about the world that I actually know. Right? So it's the weightedness of the coin, or which slot machine I'm going to play. Or it could be labels of identities of people that I'm interacting with. Like we're all professors or students, and this guy's a doctor, and that person's an engineer or whatever else. Okay? So these are denotative labels. I'm going to layer on top of that the fundamental and transient sentiments. Okay? I still have the same model, except now I've got fundamentals and transients up here, and they're connected to so this is my connotative state. This is my denotative state. My connotative state so this new piece has three important components. The first one shown in red is the connection between fundamentals and transients, and that's the affect control principle. Okay? It's governed by this parameter alpha, which says how strongly do I believe that people are going to act according to the affect control principle. So that's the first one. The second one is that I also have a model of how fundamental sentiments change over time. Okay? So, and that's again a probability distribution, and it has a parameter beta. So beta is not so important for us right now because we probably believe that fundamental sentiments change very slowly. So beta will just be very small, won't have a big effect. The third piece is a probabilistic potential that connects the connotative and the denotative worlds together. This probabilistic potential, this G hat, Neil and I are calling the somatic potential. Okay? The somatic potential allows me to relate my representation of everything in the world, everything that is denotative, with my sentiments about all of those things. So, given these three pieces, I can carry out exactly the same calculations that I was doing before. Right? There's no difference between this model and the previous one. All right? And the calculations are a little bit more complicated, but basically that's exactly the same as what we've done already. So what is this somatic potential? Okay? This is a way of visualizing it. You can imagine a two-dimensional space where this axis is the connotative space, so these are my sentiments. So this is E, P, and A. And this is my denotative space, which is maybe a list of labels of all the actions that I could take. Okay? But it could be anything else. It could be a continuous value. The somatic potential is a function, a probability distribution in this two-dimensional space. Okay? It's actually not two dimensions because this is three-dimensional, so it's actually four dimensions, which you can't visualize as a Scottish mist, but never mind. Okay, so how does this work? If I stand on this denotative axis and look down the connotative axis, okay, I'm looking down one of these pink lines, that's your ACT dictionary. Okay? One value of the denotative space is an identity. This pink line is a distribution over all the sentiments. Right? And this is done by going out and measuring them. So you measure it, and maybe I have a bunch of samples. So here's one that's fairly peaked. Here's one where there's some disagreement. So some people said it was positive, and some people said it was negative. So it's multimodal. If I stand on the connotative axis and look down these red dotted lines, this is like imagining that you're at a point in the EPA space and then looking around and seeing all the identities that are near that point and ranking them by how far away they are from that point. Okay? So I can construct a probability distribution over denotative labels given a connotative state. So the transform, or the potential, defines a transform that allows me to go between one and the other seamlessly. And we believe that this embodies Neal's principle of inextricability. This thing is there, it ties these two pieces together, and once you have a sentiment, you immediately call forth all of these denotative identities that are related. And if you have a denotative label in the world, you see something happening, you see a guy with a white coat in a hospital, it immediately calls forth the sentiments that are associated with that person. Okay, so how does this help us? Here I've drawn, sort of hacked in our denotative plan tree with all the possibilities that I have to think about, and every single one of those possibilities has got a distribution in this EPA space. I've drawn here in red the distribution of my expectation. So this is what I expect to happen in the connotative space. I'm in a hospital, I expect people to behave in a certain way, for example, right? So that's this distribution. Then what I can do is I can project this red distribution through all these pink lines, and that's going to create a probability distribution over the denotative labels, telling me what are the things I can do right now that are most aligned with the situation that I'm in. And then what that allows me to do is it allows me to disregard some of these branches. Like this dashed one here, it doesn't line up, right? It's the sentiments that are associated with it don't line up with my expectations, so I'm just going to disregard it. Okay? So what that allows for is it says, well, now I can ignore some of these branches, and I'm ignoring them for a very good reason. I'm ignoring them because if I took that branch, it would lead me into a misaligned situation. And misaligned situations are not helpful to anybody, right? We all wind up fighting, and it's all bad. Okay? So I don't even have to think about it, right? I don't even have to consider it. So I never let that enter into that plan tree. Okay, so there's the plan tree, and what this is doing is essentially, now imagine the plan tree is in the dark. I can't see it anymore, and the affect control principle, these sentiments, are like shining a beam of light down this tree. That beam of light is not the width of only one branch, okay? Because of all these probability distributions, it has a certain width, right? And that width says it's going to illuminate just a couple of options. And those couple of options are the only ones I'm even going to think about, right? This is important. It's not that I'm going to think about them all and then rank them according to this flashlight beam. The flashlight beam is only showing me the ones that are going to be aligned. Okay? So this solves the problem. It allows me to now construct this tree in a way that's very directed and basically going according to how I feel the alignment should go in the situation. Okay. Right, so that is the core, that is the most important thing about Bayesian that I wanted to get through to you today, is that connection between the connotative and denotative. Okay. Okay, so I'll just run through, actually maybe I'll skip this, we can talk about this tomorrow because I want to show the demo as well. Some of the differences between Interact and Bayesian. There's some additional Bayesian bits. Re-identification is now done on a per sample basis. Basically, by adjusting the parameters, we decrease the strength of the affect control principle and increase beta, which is how much we believe things are going to stay stable over time. And what this does is automatically repopulate the denotative state with a whole host of identities that are related and are more in tune. So if things go really wrong, the sampler that I've shown you breaks down, and in order to recorrect it, I repopulate it with samples that basically agree with my transient impressions, right? I say, well, okay, this guy's not a doctor after all, he's doing this weird thing, so I'm just going to now repopulate my denotative state with some new identities for it, okay? So it happens on a per sample basis, so that means you don't just have to select one new identity, you can select a whole host of them, okay? And we can show this tomorrow in the demos. Institutions are now part of this X variable. We can talk about that as well later. We can do learning of these somatic potentials, and there's also a fully implemented emotions model in there. And in this case, emotions are differences between fundamentals and transients. And they either create emotional signals being sent by other people that I can observe, or I can send emotional signals to other people. OK, so in the last 5 minutes, I'm going to introduce the prisoner's dilemma to you, and I'm going to show you a quick demo. So this is my minimal in computer science. Computer scientists always look for minimal working examples. Okay? The prisoner's dilemma is the minimal working example that shows you both this denotative expectation, this utility maximization element, and these sentiments. So here's Aria, and you're going to play against her. And the game is there's a big pot of coins that are neither yours nor hers. And at every step of the game, you get to either give her 2 coins or take 1 coin for yourself. She has the same choices. You don't reveal the choices until they're made, and then the choices are revealed and the coins are distributed. Okay? This is an interesting example because the best thing we could do is cooperate with one another, and we'd both get 2. But then, of course, if I cooperate with her and she takes 1 coin, then she gets 3 and I get nothing. Right? So if she's going to do that, well, then I'm not going to give her 2. I'm going to take 1 myself. Right? And then we both wind up with 1. The rational solution to this problem is for everybody to always defect all the time, and we fail as a cooperative group because we're not playing this cooperative solution. OK, so this is the game tree for that game. And I can see here at the root, I know it's kind of small, but at the root is up here. I have 2 options, give 2 or take 1. And then she has 2 options, take 1 or give 2. And I'm going to rank those equally. OK, I don't know what she's going to do. 50-50 chance. I can compute the values. So this is 2 steps of this game. I can compute the values and figure out in boldface that the best thing to do is for me to take 1. So this is the Homo economicus solution, right? It gives me what I should do if I'm just going to be a rational agent. In fact, the Homo economicus solution is a little bit more simple because I'm going to also assume that she's playing rationally, in which case the probability that she's going to give is 0 because she's going to play the rational solution. And so I can cut that branch off. So that's in those observations. I'm going to cut off the ones that are really unlikely, right? And I'm just going to focus on these ones. But again, in this case, I always have to consider both of these options, right? I can't get away from that. OK, what does Bayesian do? Well, first of all, we need to know who we're up against. So let's say I'm a friend and I'm playing, she's my friend. Then all I get is a single action. This is the only thing. I wouldn't take from my friend. So I'm going to give to my friend, right? And so all I see is one possibility, which is give her 2 coins. And then I have a probability distribution over her axis. She's my friend. She's probably going to give to me. But maybe she's, I don't know. You never know, right? There's a small chance maybe she's going to take. So I can do the calculation, and I'm going to give to her. Maybe we're enemies, though, right? And then if we're enemies, then the only thing that occurs to me is to take. I'm not going to give my enemy anything. And then in that case, the game tree looks like this. OK, how much time do I have left? 4 minutes, right? Just enough time to show the demo and then wrap up. OK. All right. Let's see if this works. Oh, I haven't plugged it in yet.
Oh. Grab screen. There you go.
Oh, I gotta wait till it connects too. It didn't stay connected, so just give me a chance, a second, and we'll see if I can connect to my hotspot here. And then we'll get the demo up and running. Okay, so I'm going to play a little game of Prisoner's Dilemma against Aria. And she should say things to us too.
I am generally a happy person.
Okay, so she's running, she's starting with an identity of friend, right? She's a friend and I'm a friend. So remember, the Bayesian model is in her brain, and she thinks she's a friend.
Please hurry up.
Okay, so Aria is actually a virtual human that's built by a group at the University of Colorado and in the Interactive Assistance Lab, and they actually build this virtual human to help people with a variety of different cognitive disabilities. So it's a medical application, and we're actually using this virtual human as well in the Alzheimer's project. But here we're using her for a little bit of fun, and we're going to play this game against her. So she's joyful. So what should we do? Should we give her 2 or take 1? Remember, she's our friend. Give 2. Okay. And now we can also send her an emotion, which are represented by these different emojis. So should we be just contented? Okay.
This is very pleasant.
So she gave 2, and she sent us an emotion. She displayed it on her face. You might have missed it because it kind of goes a little fast. She's joyful. She still thinks we're our friend. She's our friend. Okay, so let's
waiting.
I know you're waiting. Okay, so let's take 1 now. Okay, we'll throw her for a little loop. We'll take 1 and we'll look scornful.
I am very surprised.
So now she's awestruck, unfortunately. There's a little thing there. And she's now labeled us as a psychotic. Okay, so she's re-identified me as a psychotic and herself as a little sister.
I'm done.
Okay? So she's now a little bit confused about the situation. And so what do we do now? Should we be sorry and give her 2? Give her 2 and we'll give her 2 and be remorseful.
I am enthralled about what just happened.
So her emotions are a little wacky. She's still awestruck, and she still thinks we're a psychotic. But there she took 1, right? So now all of a sudden she switched. See, now all of a sudden she realized, oh my God, I'm playing against a psycho. I'm going to take 1. Okay. So we can keep going, but given the time, and Kim's looking at me like I got to get moving here, so I'll go back and wrap up. We can play with that some more later if anybody's interested. Okay, so to wrap up, artificial intelligence has basically seen intelligence as being rationality. Okay? And I've tried to argue here that that's a major problem. Not just because it's going to create really weird agents. So artificial intelligence can't create agents based on this that interact with people in a reasonable way, but also that it will just not be able to do it, period, because it has to construct this giant game tree and it has no way of solving the reinforcement learning problem. But we know that emotion's necessary, and I believe that affect control theory gives this heuristic guide for social intelligence. Okay? So this is, again, important for 2 reasons. 1, it allows me to actually do anything in the world, right? Otherwise, I'd be like Phineas Gage confronted with all the slot machines, just forever trying to calculate what to do. Okay? It shows me what I should do. And not only that, the things that it's showing me are encoding a social order that allows us all to work together and solve social dilemmas, like the tragedy of the commons, for instance. Right? So it's there for a very specific reason. It's there to allow me to neglect my individualistic, core goals and always basically act according to something that's going to be solving these social dilemmas. Okay, so artificial intelligence people look at this and they go, yeah, but that's just because the human brain is so puny and we're going to build these big, huge machines and we'll be able to do this, no problem. I don't think that that is the case, and I think that the implications of it are a little bit more drastic than that even. So von Neumann and Stanislaw Ulam also coined a term they called the singularity. And the singularity, they said, is when technology starts to develop at a pace that is faster than we can keep up with it. Okay? And when that happens, that point in time, then it's a runaway chain reaction and we've lost control of it. All right? So I don't believe that that's happened yet. Well, I don't know, when I watch my kids with their iPods, it seems like maybe it has, but never mind. What I want to do is exhort to you, as social scientists, I think that you hold the key to solving this mystery, okay? And I'm going to exhort you, get involved in artificial intelligence, because you hold the answer, And you hold the key so that we don't wind up in this kind of situation, right? That none of us really want to end up in. I don't think we're actually going to end up in that situation. Okay, so I have a lot of people help me with this work, and some generous funding from a number of different institutions, including this new grant that Kim and I just got, and Tobias from the Transatlantic Partnership. And you can go to bayesian.ca. And we'll talk about the software again a little bit later, and tomorrow. Thanks.